In subtopic 9.3 we're going to look at interference of waves, and you can see that we're going to start off with Young's double slit experiment. We have already dealt with Young's double slit experiment in subtopic 4.4 on wave behaviour, so we'll link back into that and sort of just explain some of the ideas that underpin that experiment in a bit more detail, and so just sort of linking into that and developing it further. So when we looked at the at Young's double slit experiment, we did look at a couple of equations that were relevant, and we also looked at the interference patterns that were produced. Those interference patterns were first really explored by Young with his double slit experiment, and it helped improve our understanding of what light actually is, how light behaves. And it actually helped to settle an argument that was happening in the scientific community at the time, whether light was a wave or whether it was consisted of particles. The development of that understanding continued further in the 1900s, but we're mostly just going to look at what Young developed and the understanding that he was able to bring to light. And the main thing is that it provided evidence that light behaves as a wave. So that's the first critical thing to draw from Young's double slit experiment. Now, the setup of this experiment is worth having a look at. We started off with a light source on one side. I'm just going to represent that as a light bulb, just so that it's a nice easy diagram to represent. Keep in mind that this diagram is not to scale, it's just to sort of provide a bit of an understanding of the experiment that Young conducted and the observations that he made and the conclusions that he was able to draw. So the setup looked basically something like this. So we had a light source here, and that was then the light from that was then shone onto a single slit, and behind the single slits we then had double slits. Now the width of those slits and the separation of the slits was quite small, so again definitely not to scale here. Now the prevalent understanding of light at the time was mainly due to Newton's development of understanding of light. He treated light as a particle, so imagine that you've got particles that are going to sort of stream through the single slit and the double slit in that direction, or they're going to go through the single slit and the double slit in the other direction. And so what was expected at the time was that they expected to see a bright band in one spot and another bright band in another spot, so that represented the light travelling through the two individual slits, and then everywhere else in between they expected it to be dark, because obviously if light's a particle travelling in straight lines, then you'd see that light's only going to travel through the two slits and produce two bright lines on either side. And in the middle was this dark region, so very dark in the middle because there's no light there, with the two bright bands either side. Instead, what they observed was a bright region in the middle, and then either side of that were dark bands, and then we had this alternating pattern of dark and light. So this alternating pattern where there were more than two bright regions, there were multiple bright regions, which just didn't make any sense in the context of treating light as a particle. So that was the observed interference pattern in this particular experiment. That's because as the light was travelling through these slits, it was behaving as a wave. So there's some wave fronts that we can draw, and so as those wave fronts are travelling out from the slits themselves, we're going to get interference between the waves as they overlap and as they start to interact with each other. So I'll just notate some of the expected observations and how we can explain what the actual observations were. So the expected observation, as I said, was two bright bands, and a dark central region. Now, it might seem that notating that about the dark central region isn't all that important, but in the context of seeing that the central region ends up being bright, it is actually a fairly important observation. So instead, the actual observation was a bright central region. So that one observation in itself is just totally contrary to what was expected. So a bright central region with alternating dark and light bands. So that's the fundamental shape or fundamental pattern that you would expect to see if you're dealing with light behaving as a wave. And so Young was able to then explain these observations using wave theory, and a few key things to note about those observations. So the first thing, we need to go back and look at what's actually happening at the double slits themselves. So the first thing there is that light from the double slits was coherent light. Now, coherent light basically just means that the light coming from both sources has the same frequency. Doesn't necessarily mean that it's in phase, just means that they both have the same frequency. So that's what the word coherent means. But in this particular situation, while they were coherent, they were also in phase. So both producing peaks at the same time, both producing troughs at the same time. The bright regions then were where constructive interference was occurring. And if you think about the path that the waves have to travel, that can provide a little bit of understanding as to how it is that we get these points of constructive interference occurring at multiple positions. And that means that if we think about the bright central region, the path that has been travelled by both waves would be equal. So the distance that they have both travelled is the same, and so they'll still be in phase. So they've both travelled the same distance, and so they're still in phase, and as a result constructive interference will occur. When we then go and look at the next bright and dark bands, and as we continue to move out from there, we can talk about the nth order. And so by nth order, what we mean is sort of the first, second, third, fourth, and so on and so forth. So at the nth order bright region, so that's counting out from the central bright region, we would have that one wave has travelled a greater distance, and that distance will correspond to some multiple of a wavelength, and means that it's going to be n full wavelengths further. So by travelling a full wavelength further, it's going to mean that those two waves are still going to be in phase when they reach the screen. So if we consider the first order bright region, means that one wave is going to have travelled one full wavelength further. At the second order bright region, one of the waves is going to have travelled 2 wavelengths further. At the third bright order region, then we'd see 3 wavelengths further by one of the waves. Then we have the dark bands. Now the dark bands are a little bit trickier to think about in terms of how far the waves have travelled, but we can still do the same sort of thing at the dark bands, they correspond to destructive interference, and that means that the waves have to be out of phase, and if they're going to be out of phase, it means that it's now going to be a peak meeting a trough. So at the nth order dark region, and again counting out from the middle, it means that one of the waves has travelled some sort of, not a multiple of a half wavelength, because 2 half wavelengths gives you a full wavelength. It's going to correspond to a difference of n minus a half wavelengths. So that means that, let's put that in brackets. As I said, it means that the waves are going to be out of phase and destructive interference will occur. And that's a brief summary then of Young's double slit experiment. We can do a few experiments to have a look at that in more detail, and there's another little bit that we need to throw on top of that we'll see in the next video, dealing with diffraction and how that affects the interference pattern. You'll notice that there's no equations here that you need to worry about. That's all been covered in Unit 4. So this is more just making sure you've got a good understanding of how it is that Young's double slit actually produces an interference pattern of bright and dark regions.